We will continue with the analysis of sets in the real number system using the notion of boundedness. In the last session, we discussed what exactly is meant by saying that a set is bounded above or bounded below, and we saw that there are sets which are bounded above, bounded below, and bounded sets are also there, which are both bounded above and bounded below, and there are sets that are unbounded in both directions, in the up direction as well as the down direction. Now we are going to see some special bounds. See, we have seen that when we are taking a to be equal to open interval 0, 1, when then 1 is a upper bound of a. 1 is an upper bound of a. And we know that 2 is also an upper bound of a. But there is something special about 1 in this case. We can see that any element from 1 onwards in the upward direction will become an upper bound of a. 1 and any 1 plus epsilon or epsilon greater than 0 are upper bounds of a. So if you take something below 1, for example, suppose that 1 minus epsilon or epsilon greater than 0, we'll just draw this line. This is 0 here, this is 1 here, and if you choose something slightly below 1, this is not going to be, is not an upper bound. This is not going to be an upper bound because 1 minus epsilon is going to be lying to the left of 1, and not only that, we can find at least one element which is above this 1 minus epsilon in the set 0, 1. For example, suppose that if 1 minus s is even below 0, 0 itself we can choose, and 0 is greater than 1 minus epsilon in that case. Therefore, one element in A is greater than this 1 minus epsilon, and that therefore it cannot be an upper bound. If you have 1 minus epsilon lying between 0 and 1, then suppose that 1 minus epsilon lies here, suppose that 1 minus epsilon is in this interval, then we can take the midpoint of 1 minus epsilon and 1, and that cannot be, that is an element of this at A, and therefore 1 minus epsilon cannot be an upper bound. Therefore, if one we are choosing is 1 is at such a position that anything less than that is not an upper bound, and anything greater than that is always an upper bound, and 1 itself is an upper bound. Therefore, in some sense, we can say that we cannot have any upper bound for the set A less than 1, or in other words, 1 is going to be the least possible upper bound of A, and we call 1 to be the least upper bound of A or LUB. In some words, in sometimes we call this LUB using the word supremum also. We are going to differ. We are going to define this notation rigorously. What we are going to define is supremum or least upper bound. Least upper bound or LUB or supremum. Let A subset of R. Yes, a real number is the LUB of A if it satisfies the following two conditions. The conditions are the following: S is an upper bound of A. Next condition is that if U is an upper bound of A, then S is less than or equal to U. This condition is upper bound condition. This condition is least condition. Therefore, there are two conditions for S to become the LUB. See, of course, it's not very clear that whether we can use the or not, because we don't know whether the LUB is going to be unique or not. We will be proving now that LUB is actually going to be unique. Therefore, S is said to be and LUB is actually the correct usage we have to write here. S is said to be an LUB of A if S is an upper bound of A. Not only that, if U is an upper bound, possibly another upper bound, then S must satisfy the condition S is less than or equal to U. That means that S is less than or equal to any other upper bound. Example, A equal to 0, 1, the example that we have just now taken. Then 1, we can guess that 1 is the LUB of A, and another example. B is equal to 0, minus 1, minus 2, etc. Then B is not, sorry, B is bounded above by 0 and any other positive number after that, and LUB of B is equal to 0. This is also a guess. In a similar way, we can define greatest lower bound for GLB or infimum. So analogously, we are going to define this infimum. Infimum from the very word itself, greatest lower bound from the very word itself, it's actually clear that if we want to call L to be the greatest lower bound of A, then L has to be, first of all, it has to be a lower bound and it has to be the greatest. So the conditions are the following. Let A subset of R, L is the GLB of A if it satisfies the following two conditions, just as in the case of Supremum or LUB. Condition number one is that L is less than or equal to A for all A in A. That means every element in A must be greater than or equal to L, or L lies below all the elements in capital A. Second condition, if S is a lower bound A, then S less than or equal to L. That means that any other lower bound must be less than or equal to L. In this case, we say that this case, oh, that's already written there. In this case, we say that L is the GLB of A, greatest lower bound or infimum of A. Example, A is equal to the same 0, 1. Then from this we can observe that 0 GLB A. Now, we were having a confusion that whether we can say that LUB and GLB, these two numbers are going to be unique or not. Of course, another thing we have to observe is that we can find the LUB provided that there is an upper bound. We can find the GLB provided that there is a lower bound. That's an important thing that we have to observe. Now, we will show that LUB, GLB, if it exists, that's going to be unique. Let A subset of R if here so take u equal to LUB of A, show that U is unique. That means there cannot be two least upper bounds. We are going to use the same method that we were using in some of our previous classes to show that something is unique. What we usually do is we will assume that there is one more if possible, and we will finally conclude that these two things are actually the same. Suppose S is also an LUB of A. So U is already an LUB. So U is an LUB, yes, LUB. We are going to slightly modify the rules. their roles. U is an LUB, therefore U is S is an upper bound. U is LUB, and change the role of S into least upper bound means that it's an upper bound. And U is the least upper bound. Therefore, U must be less than or equal to any other upper bound. Okay, now we reverse the roles. U is an upper bound, S is LUB. But what is the relation between LUB and any other upper bounds? LUB is less than or equal to any other upper bounds. Therefore, since S is the LUB, S is less than or equal to any upper bound U, then we have U less than or equal to S and S less than or equal to these two inequalities simultaneously imply that S must be equal to U. Therefore, if LUB exists, it must be unique. In the same way, we can show that if GLB of a set exists, then it is unique. So this is a question to prove. The proof is exactly the same. The only difference is that instead of less than or equal to, we may have to change it slightly. There is not much difference. You can easily do that. There can be actually some confusion in the word supremum and maximum. We are going to define what exactly a maximum is meant for us. Maximum of a set A. A we are assuming to be subset of R. A belongs to, or in other words, since we want to use the word maximum, we will take M. M belongs to A is the maximum for A if A belongs to A implies M greater than or equal to A, or in other words, to be simple enough, A is less than or equal to M. That means that for some element of A to be the maximum, it must be greater than or equal to every other element in A. So it's the obvious intuitive definition. But is this different from the definition of supremum? Let us just go back to the definition of supremum. Here we have taken M belongs to A to be the maximum of A, and what about supremum? In the definition of supremum, we have taken L is the GLB. Okay, we are actually L belongs to R is the GLB. We should have said that is actually a missing. L belongs to R is the GLB of A, provided that these two conditions are satisfied. Therefore, we are not insisting on L to be an element of A. And in the case of GLB also, this is LUV. Okay, S belongs to R, we have clearly taken here. So S belongs to R is the LUV provided that it satisfies two conditions. We are not insisting that S has to be a member of A. So supremum need not be a member of A. But in the case of maximum, what we are defining here is we want the maximum of A to be an element of A. Therefore, the difference between supremum and maximum is that maximum is greater than or equal to every element in A, but at the same time, maximum has to be a member of A. But supremum, it's a real number. It has to be greater than or equal to every element in A, but it is not necessary that that element itself is there in A. The following example actually clarifies it slightly better. Suppose that we have A is equal to 0, 1. Then supremum or LUB of A, this is 1, but A has no maximum. But why is it like that? Maximum has to be an element of A. It looks that 1 can be a maximum, but 1 is not here in this A. Suppose that we have some element. See, definitely it has to be in 0, 1. If M lies in 0, 1, it cannot be the maximum of A. But why? M, suppose that M is in 0, 1. Therefore, M lies somewhere here. But now, m plus 1 by 2, this is greater than m, this is less than 1, and this belongs to A. Therefore, m cannot be the maximum. Therefore, in the set open interval 0, 1, there is no maximum. Similarly, we can define minimum also. Minimum is going to be some other m prime such that m prime is less than or equal to every element in A. And for the set capital A, there is no minimum also. But this set has both supremum and infimum. Therefore, the difference between maximum of a set and supremum is that supremum is a real number that is greater than or equal to every element in that set. But maximum is not just a real number, it has to be a member of that set itself or be called as the maximum. So the difference between maximum and supremum is hopefully now clear. In exactly the same way, we can define the minimum of a set also. And leaving this as an exercise, define minimum of a subset of R. Now there is a possible question. What is the supremum of the empty set? So for the set to be having a supremum, see that that must be bounded above. Is said to have infimum, it must be bounded below. But we haven't actually said these things that if a set is bounded above, it has a supremum. If a set is bounded below, it has an infimum. We haven't actually said any such thing. But it will be a good exercise, thinking exercise to think what can be a supremum and what can be an infimum for the empty set.